All right. So now we're going to talk about a slightly different sintering method known as liquid phase sintering. So as you might suggest, as the name might suggest, this one will involve a liquid phase. All of the other sintering mechanisms we've talked about so far are solid state sintering. So things are not becoming a liquid and then re-solidifying. Everything is in the solid state. So all those diffusion methods are solid. So this one's a little different, obviously, because of the liquid part. Okay. So before we kind of get going into this, I want to ask a simple question of how do you think this liquid phase is useful for enhancing sintering? Because obviously, if there is a whole topic on liquid phase sintering, then this is going to be a topic that's important and useful, and there's some benefits to it. So see if you can come up with what this will do and how it will enhance sintering. Pause the video, come back when you've kind of come up with an idea of what you think this will do. All right, so now let's look at the advantages. So like I said before, there's a reason we have liquid phase sintering, also abbreviated sometime as LPS. So if you see that, it means liquid phase sintering. So the big advantages of why we want to do this and why it's used on a commercial scale is that it provides rapid densification, right? That's predominantly what we're looking for in sintering. And it also gives us a very homogeneous or uniform microstructure. So that's important for a lot of those properties that we're looking for. And so this curve here just kind of shows the shrinkage. So densificate, another way of looking at densification versus time. And so it really shows here that the initial stages cause a lot of shrinkage, which means that we get rapid densification. So that's important for this type of sintering. All right, so let's look at how this does it. So we have a liquid phase, and this aids densification by helping to rearrange the particles. So we saw this in solid state sintering as a part of that initial stage of sintering, that rearrangement can occur. Well, the liquid phase actually helps that packing. So it helps rearrange the particles into a better packing. So you can kind of think of it as like a lubricant between the particles, allowing them to rearrange into a more optimal configuration, which has better packing. So that's going to instantly help the shrinkage and help the densification. And the other part of that that the liquid serves is that it increases the contact pressure between the particles. So we saw in solid state, there's just usually a single contact point between two particles that forms a neck and so forth and grows to become a grain boundary. Well, with these, there's a liquid between those two particles, and that can actually cause some capillary forces which aid in that pressure between the particles, and that aids in densification. So these are kind of the effects, or the positive effects of the liquid state. Okay, so just like with solid state, we're going to look at the stages that we have, and you might have seen that already on the plot in the previous slide. But the first one is that solid particle rearrangement. So we talked briefly about that, and we'll talk more about it. The second one is solute precipitation. So this is where things dissolve in the liquid and then can re-precipitate elsewhere. So we basically have liquid diffusion. And then microstructural coarsening. So this is basically the grain growth and similar types of growth that we see in solid state sintering. So those are kind of our three steps that we have. Okay. So the first part, though, that's we haven't talked about yet, is that obviously we have to form a liquid, right? That's got to be part of this process. And so a portion of our material, when it's heated up during sintering, has to form into the liquid state, right? So that could be some type of mixture of the various components forming a low temperature material, there can be a number of ways in which the liquid actually forms, but in some way the liquid has some small portion of the material has to become a liquid. But again, keep in mind that we're still talking about the sintering process, and so it's predominantly solid. There's only a small amount of liquid. But so this diagram just kind of illustrates that maybe this little bit of material can form a liquid phase at this temperature, and that basically spreads out amongst the particles. And so that first stage that we talked about is rearrangement, right? So it can aid that it could be considered this dark phase here that allows these particles to rearrange and form into closer packed arrangement due to the motion, right? The liquid again acts as basically a lubricant, allowing these solid particles to flow and rearrange more easily. Okay, so if we think about the formation of this liquid phase, a liquid can act in a number of different ways with regards to a surface or a solid. And so here's just a very simple illustration of that. We've talked about this a little bit in the past, but you've seen this hopefully in other classes as well. But if we just look at the way a liquid droplet can interact on a surface, so this represents the liquid phase and the solid particle, it can do one of two things. It can wet the surface if we have a low contact angle, theta. So basically the angle between the solid and the liquid droplet is known as theta. And if that angle is quite low, it refers to that situation as wetting, because that low angle means that droplet's going to spread out and cover or wet the surface of the solid. So this is wetting for this system. So a low contact angle. The other situation, obviously, then, is if we have a much higher contact angle between the solid and the liquid. This is where this droplet instead kind of beads up and forms a very discrete droplet, with the sort of limiting case being the formation of a sphere of that liquid on the solid, and there's really only that one contact point. And so the difference here is the amount of contact between these two phases, right? So when the material wets, there's a lot of contact area between the liquid and the solid, and then when it beads up, then it has very low contact between these surfaces. And so this is the requirement for liquid phase sintering. We need it to wet the surface for these effects, positive effects that we see to occur. So we want this low contact angle wetting case to occur. And let me show you why that is. And so I mentioned briefly the capillary forces that can occur in liquid phase sintering. And this is how that can occur. So let's imagine 3 scenarios with contact angle, or how a liquid wets. And here, instead of having one solid surface, I'm going to have 2 planar solid surfaces. So if you look at this first example, these plates here are solids. And the reason we have 2 is to indicate the neighboring particles in the powder, right? So we're just making them ideally as 2 planes just so that we can think about them more easily. But basically these are our solid particles, and then this is the liquid phase in between. So the case in the middle is when the contact angle is right at 90 degrees. And the reason I start with that is because in this case, when we have 90 degrees and 2 of these solid surfaces, what we get is basically a situation where there's a kind of metastable equilibrium. There's equilibrium in this scenario where nothing's moving. All the surface energies that we see are in equilibrium. So you can kind of see that the vertical forces here would be equal and opposite. And so the liquid would not move, and therefore the solid particles would not get further apart or closer together. And so this is not what we want to occur if we want the particles to rearrange, because in those cases we'd want them to move in some way, right? All right. So let's then look at the other scenario where our contact angle is very high, right? I already said that this is not the case that we have for liquid phase sintering. So our contact angle is really high. And so in this case, we have, now that we have two solid phases, we can see that it looks similar to the droplet. And so all of our liquid kind of beads up. And there's a natural tendency for that liquid to bead up and have less in contact with the solid. And so what that does is it pushes if you're kind of thinking about the surface energies here, those surface energies balance out such that there's a force acting to push the solid plates away from each other. So the force is basically to push the solid particles further apart so that this droplet can kind of consolidate into one sphere. And so this is obviously bad, because if we're thinking about rearrangement, we're trying to form a more dense ceramic, and this is pushing particles further apart, right? And also from a liquid point of view, all of the liquid beads up into this one small area, and so we would have to have a lot of liquid relative to the amount of solid. And so that's generally not a good idea. All right, so let's look at the case that we're actually looking for then. So here, this is the wetting case. And so the liquid is wetting the solid surface, but now we have two of them. And so it forms this concave sort of structure. And this is one in which this is actually trying to move to basically increase the contact area between the liquid and the solid. So you can kind of think of wetting as the liquid really likes the solid surface, as opposed to the other case where the liquid does not like the solid surface, so it beads up. And so in this case, there's going to be a force causing the concave to try to kind of move to the left here and move to the right here to increase that contact. And what that does is there's only so much volume of liquid, and so that creates a force causing the solid plates to move up for the bottom one and down for the top one, and that pushes them closer together, and that creates a situation where there's a force actively bringing the particles closer together. And that's the capillary force. This is the capillary force you may have seen inside of a glass tube. And this is bringing these particles closer together. So for our liquid phase sintering, this is helping us rearrange so that the particles are closer together. So you can kind of think of this idealized system, and if it happens all throughout the material, then it's bringing everything as close together as possible. The other point about this situation is that much less of the liquid is required because we can form a very thin layer of this liquid between the particles, as opposed to this where we have to have a lot more liquid in this scenario. So basically this capillary force, along with that sort of lubricating effect, helps us rearrange particles. And so that's why if you look at these different phases during sintering, that's why this particle rearrangement actually plays a huge role in the overall densification of the particles. All right, so next we want to look at that middle stage where we have solution precipitation. And so that's, again, another benefit of this liquid phase. So if you think about this liquid phase, it obviously formed from this material, and it can dissolve some of the solid of the materials. So if we look at something like this silicon nitride, which is commonly liquid phase sintered, we have this glassy phase or liquid phase in between. There's the capillary force, a very thin layer of the liquid drawing these particles together. So we've already had that rearrangement occur. And so now what happens is we have this liquid, and this liquid, say on this region here between this very thin layer of the silicon nitride particles, can dissolve the silicon nitride. and that silicon nitride can, once it's dissolved, it's in this liquid, and therefore uh, liquid diffusion is rather quick. And so the liquid can diffuse easily from this region here through the liquid to the necked region down here and redeposit or reprecipitate away from that force here. And so again, we tend to think of diffusion as this random process. And that's true when it's self-diffusion. But in this case, if we think about this area here, there's a huge force from the capillary force that's pushing these particles together at these thin regions here, here, and here, right? So there's basically a force kind of pushing this together. So that gives us a chemical potential. And so there's less of a force in this junction region down here because there's a lot more liquid and a lot less capillary force. So basically, this chemical potential pushes that solute from this region down to this region. And so it basically forms a liquid here. So it removes solid matter from here and it moves it to here where there's less of a chemical potential. And so that gives us that rearrangement and gives us that densification that we're after. And it does it all in this liquid phase. And so that gives us this middle region where there's a slowdown in densification, but there's still increased densification happening due to this solution reprecipitation mechanism. Okay, so those are the main two methods for which liquid phase sintering gets its advantage. And you can see that after those two methods are done, there's only minor densification happening with this last phase. And that last phase is known as skeleton sintering, but this is basically just solid state sintering. So basically just imagine the liquid is really not doing anything at this point. And so it's just by our traditional means of solid state sintering, we have grain growth occurring. So the grains will obviously get larger in this state. So this is really not as important because the bulk of the densifications already occurred. And so that decreases rapidly. And this one isn't as critical during liquid phase sintering. All right, so let's kind of recap this liquid phase sintering and think about some of the conditions that are going to be useful or important for this type of method. So obviously, we have to form a liquid phase, and there has to be solubility of the solids in that liquid phase, right? Otherwise, we can't move material away from those contact regions with solution reprecipitation. And then also, we have to have that capillary pressure. And that capillary pressure is related to the particle diameter. So basically, if we want this to occur more rapidly, we want smaller initial particles. So typically, we want as small a particle as possible. We also have to have a big one here. We talked about that wetting, right? The very low contact angles. And so we need that liquid that's formed to have a very low contact angle with the solid phases, and therefore it wets. That's a big condition here. And there must be enough liquid to wet the entire solid phase. So we have to form enough to do that. So, there's a lot of advantages, but keep in mind when I initially talked about some of the properties that we can get for sintering, having this liquid phase, obviously we've seen it's great for rapid densification and so forth, but having that liquid phase, right? If we have a high temperature application, we can run into the influence of that glassy or liquid phase at lower than normal temperatures. So these are typically not going to be used for high temperatures because we now run the risk of liquefying that glassy phase in between the phases, in between the solids, and that can reduce mechanical integrity. So we can decrease creep resistance and so forth. And so those are all issues that we have to think about.